Let's think back to our youth. Back to the time when we had wonder about how the world worked. A lot of the questions you probably asked were why questions. Why does the sun shine? Why is the grass green? Why do some things taste sweet and some don't? A lot of these questions probably weren't answered to the extent you wish they were, or they weren't at all. However, all of these answers are made up of just four things. Four fundamental forces. These are electromagnetism, gravity, the weak interaction, and the strong interaction. All of these forces act similarly, using their own gauge bosons. Understanding each of these gauge bosons is fundamental to understanding the force itself. Let's take a look at this action. Bat, ball. I'll be right back. Okay, so all of the movement experienced by the ball can be chalked up to electromagnetism and gravity. Let's see why.
We all know electromagnetism because of the fact we've committed to memory. Opposites attract. And we all know gravity is the reason we stay on Earth, why we orbit the sun, and why Isaac Newton got as famous as he did. But why do these forces act the way they do? It's all up to their gauge bosons. In electromagnetism, there's photons. Charged particles constantly emit them, and when they are emitted from and hit particles with opposite charge, they bring them closer. Opposites attract. Particles with the same charge are repelled in this way. This happened in our action. The electrons from the bat emitted photons that hit the ball's electrons and sent it flying. Like how electromagnetism has photons, gravity has what are called gravitons as its gauge boson. Gravitons have actually never been detected, but they fit pretty well into the theories and are accepted. Similarly to how charged particles emit photons, anything with mass constantly emits gravitons and brings things with mass closer together. This happens with our ball. The ground constantly emits gravitons, bringing the ball back down to the earth, bringing an end to our action.
Those two forces more or less describe what happens when objects move. But if we look very closely at these objects, the atomic nuclei, then we'll find the final two forces, the weak interaction and the strong interaction.
The weak interaction is the only force that interacts with the flavor of particles. They do this by using their massive gauge bosons W and Z particles. The W's are charged while the Z's are neutral. Take these quarks for example. The positively charged ones called ups, tops, and charms, and the negatively charged ones called downs, bottoms, and stranges. The weak interaction can change these particles into one another in processes like beta decay. In beta decay, a neutron decays into a proton, an electron, and an electron neutrino. A neutron is made up of two down quarks and one up, while a proton is made up of two ups and one down. So one down quark is turned into one up. And due to the charges of the particles, a W- particle must be emitted. The W- quickly decays into a negative electron and an electron neutrino. Combining these two reactions gives the net equation for beta decay. The last force is the most mysterious in terms of what we know about it. Strong interaction is the force that holds together quarks and protons and neutrons, and what holds those together in a nucleus. The gauge bosons in a strong interaction are rightly named gluons, holding everything together. However, this force and the gluons themselves go against logic and are shrouded in mystery for this reason. All other forces are stronger when the acting bodies are closer together. However, the force gluons emit actually gets stronger with greater length. Science still doesn't quite know how or why.
The world can be effectively summed up using these forces. Scientists are still trying to find out things like how gluons work. Even though there's a lot of scientific knowledge, don't be discouraged from asking why questions. There's still a lot of unsolved mysteries out there.